In the previous part, I have shown you how to calculate the exact atomic molecular weights for the protonated, saturated, and hydrated species of the ethylene oxide and polyethylene oxides macromonomers. Right now, we're going to continue in the same manner, but we are going to calculate the exact masses for the ethylene oxide derivatives. As you can see, the Brito formula for the sulfated, disylated ethylene glycol is different from ethylene glycol itself, and it's not C2H6O2 but C9H12O4 sulfur. What we're gonna do, to calculate the exact masses for this species, we're gonna make a really slight modification of the Excel table. First of all, I want you to remember this Brito formula. We're gonna go to the Excel file and we're gonna copy the whole table that we have created previously. We're gonna create a new sheet and paste, Control A, Control C, and sheet 4, Control V. So instead of C2, we're gonna put C9. Instead of H, we're gonna put H12, O4, and sulfur. We're gonna create a new column for the sulfur, and for the first macromonomer, it's gonna be 1. For our convenience, I am planning to delete everything that is below previously calculated data. We're gonna make a few adjustments to the calculation of the molecular weights equation. We're gonna leave carbon B, hydrogen C, and oxygen D columns, but we also are going to add this sulfur column, the E column. Since we have 1, yes, E2, and we are going to multiply it on the atomic weight of this sulfur using the very same program that I showed you before. And exact mass of the sulfur is 3197. We copy it, we paste it in the Excel file, and close the brackets, press enter. This is how the this is the exact mass of the molecule, and this is since we left the equation for the rest of the equations for the rest of the columns, we still have the exact masses of the protonated molecule, protonated hydrates, sodiated, and sodiated hydrates, which is really convenient. All we have to do is just to make sure that in the next for the next macromonomers, we have carbon atoms increased on 2, because ethylene oxide has 2 carbon atoms, which is going to be 11. For the hydrogen, we're going to make an increase on 4 atoms, because ethylene oxide has 4 hydrogen atoms, which is going to be 16. For the oxygen, we only add 1 oxygen, because ethylene oxide has only 1 oxygen, and sulfur remains the same. So actually dragging and dragging these 2 cells will increase the further macromolecules contents subsequently, and as you can see, each other macromonomer has increased on 2, which corresponds to the ethylene oxide units, which is correct. So we just drag these columns down. For the hydrogen, we're gonna see the increase on the 4 hydrogens, because any ethylene oxide has 4 hydrogens plus. And for the oxygen, we only increase on 1, because ethylene oxide has only 1 oxygen atom. I'm sorry. It was 4 and it remained 4, so that's gonna be 4 for all of them. No, wait a second. It was 5. Sorry. Sulfur remains the same because it corresponds to the 1 totally group. Subsequently, similarly, we drag the exact masses for each macromonomer, and here how we get the exact masses of the macromonomer. Each macromonomer containing 7 ethylene oxide units, 15 ethylene oxide units, or, as in our case, 65 ethylene oxide units. Next, we do absolutely the same thing to the other columns, just simply dragging them down. And thus, for the protonated ethylene oxide macromonomer containing 7 ethylene oxide units, we have the mass of 4481. This is the mass which is going to be detected. Remember that only charged molecules can be detected, such as protonated or protonated hydrate, sodiated or sodiated hydrate. Got it? And in your case, please check these values of 3000 and more. This is what you have to correspond or find in your mass spectra. Similarly, we are going to, well, and this is how you find the exact masses. Please feel free to ask me any questions regarding that. But we're not finished, and I am gonna show you how to make the same calculations for the azide, just to make sure that you understand it. Now we go back to the molecular weight, to the Brutto formula of the azide, which is this. And as you can see from this structure, the very next macromonomer will contain another ethylene oxide unit, and all you have to do is just to draw these 2 carbons, 4 hydrogens, and 1 oxygen mole. But we are gonna start with the molecule of C2H5N3O4 as the source of this row of these segments. It's really easy to remember, and we go back to the charts. It is C2H5O1 and N3. We have to make the adjustments for the calculation of the atomic weight, of the molecular weight, and this is what we're gonna do. E2 multiplied on atomic weight of the nitrogen. The atomic weight of nitrogen is calculated, is found in the exact mass calculator, which is 14. We copy it, go back to the Excel, paste it in the equation, press enter, and this is how we get the exact mass of the absolutely neutral molecule. As you can see, the protonated mass has been changed. Subsequently, protonated hydrate subsequently has been changed as well, and this is the convenience of the Excel. Please make sure that the next macromonomer containing 2 ethylene oxide units has 4 carbon atoms, because it is 1 ethylene oxide more, plus 4 hydrogens, which is going to be 9, plus 1 oxygen, which is going to be 2, and this very same amount of the azide, because it is azide derivative and it doesn't change from the one fraction of the macromonomers to another fraction of the macromonomers, from one macromonomer to another. The number of the atoms, the number of azide groups remain the same, and this is why the N remains the same. Now you may drag it and see how the azide remains the same. Oxygen is increased by one from one to another fraction, from one to another molecule. Hydrogens has been changed on 4 and the carbons has been changed on 2. You drag it to the end of the chart, and similarly you drag the remaining tables, the remaining columns, and this is how you get the mass of the neutral azide derivative of the polyethylene glycol of the 3000 molecular weight. This is the protonated one, and this is what you're gonna most likely to detect. This is the protonated hydrate of the molecule. This is the sodiated, and this is the sodiated hydrate. I think it's pretty clear, and now you may use it yourself. Please feel free to ask me any questions again, and it seems to me it's gonna be really easy for you to calculate the molecular weights. Atomic molecular weights, exact molecular weights from now on. Good luck, and let me know what's going on with your mass detection.